Welcome to session 10, where we look at routing fundamentals and subnetting. If you're going to be a successful network engineer, subnetting is something that you really need to get grasp with. At the end of the session, we'll be able to list the 4 layers of the TCP/IP model, describe the functions of each layer, which you have done, in the previous sessions, and also understand the functions of reserved IP addresses. There are a number of key topics: routed protocols, IP routing, and the mechanics of subnetting. The reading list is as shown. So, routed protocols. A protocol is simply a set of rules that determine how computers communicate with each other across networks. A protocol describes the following: the format that a message must conform to, the way in which computers must exchange a message within the context of a particular activity. Routed protocols. A routed protocol allows a router to forward data between nodes on different networks. It must have the ability to assign a network number and a host number to each individual device. These protocols also require a network mask or subnet mask in order to differentiate between the network and the host portion of the address. A network contains an IP host address and a network address. Both are required to have a routed network. A network mask is used to separate the network and the host portions of the 32-bit IP address. The ending process produces a network address that identifies the interface the data must be routed out onto to reach its destination. This slide shows you an example of how the network addresses, or the host addresses and the network addresses, and the role of the router in all of this, and how the masking is done. Data encapsulation is a process whereby information is added to the frame from each layer of the OSI model. This is also called packet creation. Each layer communicates only with its peer layer on the receiving device. When a host transmits data across a network to another device, the data goes through an encapsulation process, which means it is wrapped up with protocol information at each layer of the OSI model. Each layer communicates only with its peer layer on the receiving device. To communicate and exchange information, each layer uses what is known as a protocol data unit. Each PDU attaches to the data by encapsulating it at each layer of the OSI model, and each has a specific name depending upon the information provided in the header. How the encapsulation works? At the transmitting device, the data encapsulation method works as follows. Each information is converted to data for transmission on the user information is converted into data for transmission on the network. Data is converted to segments, and a reliable connection is set up between the transmitting and receiving hosts. The segments are then converted into packets or datagrams, and the logical address is placed in the header so each packet can be routed through an internetwork. Packets or datagrams are converted to frames for transmission on the local network. Hardware addresses are used to uniquely identify a host on a local network segment. The frames are converted to bits, and a digital encoding and clocking scheme is then used for that. The diagram shows you in brief how all of this information. So what you can see is, for example, your email, is some form of data. Then at the next level, further data is added. And then at the next level, the network header is added. And then at the next level, you add a frame header. And then that is then converted into binary ones and is transmitted. These are bits which is transmitted. And then at the receiving end, a reverse process is followed to recover the original data. The transport layer also does some segmentation, sequences, and adds error checking to the message. The network layer source and destination address are also added to the datagram. An ARP cache provides a MAC address for the destination IPs. So the Ethernet frame is added with the source and destination addresses. So this is what happens at the transport layer, and this is shown diagrammatically, the way it works. The Internet protocol we know is widely used networking scheme. It is connectionless, unreliable, best effort delivery protocol. The IP does not verify that the data reaches its destination, so it sends it and it forgets it. It has no responsibility to check that, oh, has it actually gotten what I've sent, has it actually gotten to where it was intended? Data here is encapsulated into packets, also known as datagrams, at the network layer of the OSI model. When the data is received from the upper layer protocol, the network layer appends the IP header information to that data. Let's look at connection-oriented versus connectionless networks. Connectionless networks are also referred to as packet switch processes. This includes IP protocol and the internet. And then the connection-oriented networks are referred to as circuit switched processes. A connection with the recipient is first established, and then the data transfer begins. TCP layer 4 connection-oriented reliability services to TCP adds layer 4 connection-oriented reliability to IP services. The IP header, has a certain length which indicates the datagram header length. This in 32 bits. You may actually pad. So if the data is not enough, you may add extra bits to ensure that you have that 32 bits or multiples of it. There's a 3-bit field which is known as a flag, in which 2 low order bits control the fragmentation. And that is shown in the diagram how the distance is divided, what happens at each layer, and what is added. Routing, we said, is a layer 3 function. It's the process of finding the most efficient path from one device to another. The primary device this is used for this is a router. So this is the network layer thing. So IP routing protocols. With a router is a network layer device, layer 3, that uses one or more routing metrics to determine the best path along which network traffic should be forwarded. Routers make logical decisions regarding the best path for the delivery of data. The encapsulation and de-encapsulation process occurs each time a packet transfers through a router. This process breaks up the data stream into segments, adds the appropriate headers and trailers, and then transmits that data. The de-encapsulation process is the opposite process. That's removing the headers and trailers and then recombining the data into seamless stream. The diagram you now see on screen is an example of how the routers are done. So if you needed to route some information from, let's say, X to Y, say X to Y, for example, it might go through A, then B, or possibly C, and then to Y. And then it tells you what is done at each level. At X, this is what is done, the functions that are done. At A, what is done. Now, note, and B and C, what is done at these routers. The question I'll put to you is, why are the layer 7, 6, 5, and 4 layers not included under A, B, and C? That will be the question. Let's look at the difference between or compare routing versus switching. Switching occurs at layer 2, routing at what? Layer 3. The layer 2 switch can only recognize its own local MAC addresses and cannot handle layer 3 IP addresses. Layer 2 switch interconnect segments belong to the same logical network or subnet. Layer 2 switching takes place within the LAN, whilst layer 3 routing moves traffic between broadcast domains, which can be in different networks. This requires a hierarchical addressing format provided by layer 3 addressing scheme. Each computer and router interface maintains an ARP table for layer 2 communication. ARP table is only effective for broadcast domains that it is connected to. The router also maintains a routing table that allows it to route data outside of the broadcast domain. Each ARP table contains an IP and MAC address pair. This diagram shows you, or tries to show you, the differences between routing and switching as far as the use of routers is concerned. You can study that diagram to see how the information is stored in ARP tables and so on. So we have said that layer 2 switch can only recognize its own local MAC address and cannot handle layer 3 IP addresses. When a host has data for a non-local IP address, it sends the frame to the closest router, also known as a default gateway. The host then uses the MAC address of the router as the destination MAC address. Another difference between switched and routed networks is that switched networks do not block broadcast. Recall that switches have larger broadcast domains. They only segment into collision domains. Routers can block LAN broadcasts. Because routers block LAN broadcasts, routers also provide a higher level of security and bandwidth control than switches do. The table here shows you some features of both routers and switches, and tries to compare them. So if you take a speed, for example, how does a router compare with a switch? If you take the OSI model, the difference, and so on. Router protocols transport data across a network. Examples of router protocols are the IP protocol, the Internet protocol. There's a novel Internetwork Packet Exchange Protocol, the IPS. There's a DECnet, AppleTalk, the Xerox X and S protocols. These other ones, you may not be very familiar with them, but they used to be quite popular. The diagram here shows you how a router transport data, how a router protocol can transport data from one end station to another. So you can look at that and then see that, so you can see how it follows, the paths it follows. It's quite similar to an earlier diagram we saw, but that one was more detailed, giving you the IP addresses of the intermediate routers. So routing protocols allow routers to choose the best path for the data from source to destination. Routers also use routing protocols to exchange routing tables and share routing information. Routing protocols enable routers to route the routed protocols. Examples of routing protocols would include the RIP, the IGRP, the OSPF, the BGP, and the IEGRP. It's important that you actually understand these protocols and know how they work and the differences between all of them. How do we determine path? Path determination actually occurs at the network layer. It enables a router to compare the destination address to the available routes in its routing table and then to select the best path on which to forward the data. Routers learn of these available routes through the static routing or dynamic routing. So routes can be configured manually by the network administrator, the ones that are called static, and the rules that are learned by others using a routing protocol are called dynamic routes. Each router that the packet encounters along the way is called a hop. So you hear normally talk about the number of hops, So the hop count is the distance that is traveled, not the physical distance, but the number of hops. Routers use routing protocols to build and maintain routing tables that contain route information. In other words, if you have several hosts on a network, the routing table will tell you which routers to go through in order to reach a particular host. Routers keep track of important information in their routing tables. This includes the protocol types, the destination next hop associations, the routing metric, and then the outbound interfaces. Routers communicate with one another to maintain their routing tables through the transmission of routing update messages. Routing protocols often have one or more of the following design goals: to optimize the system, simplicity, robustness and stability, and then flexibility. Routing algorithms use different metrics to determine the best route. The most commonly used metrics are bandwidth delay, load reliability, hop count, ticks, and cost. Now, what are the advantages of each of these methods? You simply don't have to know that they use bandwidth delay or low reliability, but what is it and what are these advantages or disadvantages? Two types of routing protocols are the interior gateway protocol, the IGP, and the exterior gateway protocol. The IGPs will route data within an autonomous system, and then the EGPs will route data between autonomous systems. So one routes within and one routes between. Examples of IGPs include the RIP or the RIP version 2, IGRP, EIGRP, and then the OSPF. An example of EGP is a BGP. Now, let's talk about link state and distance vector. The IGPs can be further categorized as either distance vector or link state protocol. The distance vector routing determines the distance and the direction to any link in the network. Routers using the distance vector algorithm send all or part of their routing table entries to adjacent routers on periodic basis. In the link state algorithms, they typically would use their databases to create routing table entries that prefer the shortest path. The link state routing protocols respond quickly to network changes, sending trigger updates only when a network change has occurred. Examples of the distance vector protocols are the RIP, which is the most common IGP in the internet. The RIP uses hop count as its only routing metric. RIP cannot route a packet beyond 15 hops. The interior gateway routing protocol, IGRP, was developed by Cisco to address the issues that were associated with routing in large heterogeneous networks. So we are saying that the RIP cannot go beyond 15 hops. So if you wanted to do more than that, what do you do? So the IGRP was a response to that. The enhanced IGRP is also a Cisco proprietary IGP and has many of the features of the link state routing protocol. It provides superior operating efficiency such as fast convergence and low overhead bandwidth. What do we mean by fast convergence? The answer is in the routing tables, the updating of the routing tables. Think about it. Because of this, it has been called a balanced hybrid protocol, but it really is an advanced distance vector routing protocol. Examples of the link state protocols include open shortest path, immediate system to immediate system IS to IS, which is used for router protocols other than IP. We have previously discussed subnetting in the last, therefore the rest of this is left as a reading assignment for you to complete. Thank you for listening.